Indian Society of Heating, Refrigerating and Air Conditioning Engineers, ISHRAE, stand tall in the Indian industry with over 10,000 professionals as members and almost an equal number of student members. Founded in 1981 and headquartered in Delhi, we operate from chapters and sub-chapters spread all over India, bringing our entire industry together. Individuals become members of our society according to their professional and academic standings. Our roadmap of the future looks very bright, with thousands of new members joining this technical society every year and bringing in a fresh outlook to our industry intelligence. ISHRAE disseminates knowledge through its technical committees, which consists of some of the best minds of our industry. It publishes technical books, newsletters, and a prestigious journal, distributing the wealth of knowledge to all its members. Working with government departments, ISHRAE helps formalize industry codes and standards. ISHRAE promotes research by offering financial support to student members to carry out groundbreaking work in technology, systems and processes. Our educational wing, ISHRAE Institute of Excellence, organizes training programs and workshops to help members enhance their skill sets. Our specially designed certification programs under ICP, that is, ISHRAE Certified Professional, empower professionals to always be in step with the prevailing technology. Specially designed courses for technicians are offered to meet the ever-increasing demand for a skilled workforce. ISHRAE organizes exhibitions, conferences, panel discussions and product presentations throughout the country. We organize the industry's largest international exposition in South Asia, ISHRAE India, to showcase the cutting-edge technology, innovation and provide a platform for closer interactions amongst the decision makers in the industry. The ISHRAE exhibition is now growing from HVAC and R show into BFA, Build Fair Alliance. This brings together several allied shows connected with the building services industry all at one location. Our chapters organize several other popular events like ISHRAEConf in Delhi, Raycon in Kolkata, Symposia in Mumbai, TechFest in Goa, and many more. We are committed to provide training and career guidance to our student members through seminars, lectures, quiz contests and site visits. A-Quest, a prestigious quiz competition organized by ISHRAE to catalyze the transformation of the budding engineering professionals. ISHRAE provides a platform to potential employers to select student members for careers in HVAC and R industry at the ISHRAE Job Junction. Young minds are made aware of the need for saving power, clean air and sustainability. The K-12 initiative of ISHRAE focuses attention on school students' development to inculcate a scientific fervor and help develop them into responsible citizens. Speedy information is imperative to keep moving forward in this hyper-connected digital age. Searcher, a specifically designed search engine, is now available, which allows access to a well-catalogued database on HVACR and building services industry with just a few clicks. ISHRAE cooperates with various national and international bodies, industry, governments, academia, think tanks to promote the concept of sustainability, environmental protection and energy efficiency and conservation. To enter and explore the universe of the Indian HVACR industry, log on to ISHRAE.in that unfolds a panorama of information Let us engineer a sustainable future together through ISHRAE.
Am I audible, sir?
Yeah, you are.
Okay.
You are audible.
So, good evening. Thank you, everybody. Thank you, all the panelists, all the attendees, to joining this program. As you know, that today we have we are going to cover the workshop on piping distribution, selection, and friction loss, and we have expert on that, Mullikant sir. So, firstly, I would like to thank Mullikant sir for taking out their time in his busy schedule. And on behalf of Delhi chapter of ISHRAE, we welcome Gaurav sir. He's from IntelliGreen. He's the managing director. Thank you, sir, joining this panel. Also, Vikas Jha is from from IntelliGreen. Our program chair is there in the panel, Valula Sidki, and Purnima is also there with me. So, further any delay, I request Gaurav sir to start this program. I mean, share some knowledge. He has some PPT with him. So I request you to share your PPT with your knowledge, sir.
Thank you. Thank you, and welcome everyone. Good afternoon, and welcome everyone for this session. And I mean, to start the session, I would like to share the technology through which IntelliGreen technology is working. And I mean, this is purely our indoor air purification. So I would like to introduce the concept in a brief time. So for that, I would like to share my screen, and I'm sharing the screen also so as to present. So I hope my screen is.
Yes, sir. Fine.
Fine. So let me just give a quick introduction about ourselves. We are IntelliGreen Technologies, and we are working into indoor air purification field from past 5 years. And I mean, like, we have successfully deployed our solutions to various prestigious clients. The technology is completely a zero ozone based comprehensive solution to improve indoor air quality. And this comprehensive solution includes active air purification, passive air purification in form of filtrations, and live monitoring of all the indoor air quality parameters. So when we talk about indoor air quality, these three parameters in indoor air are at most concerned. These are microbial contamination, the gaseous contamination, and the suspended particulate matter levels. So all kind of bacteria, viruses, pollen, mold, yeast, allergen, fungus comes in form of microbial contamination, harmful volatile organic compounds as contamination and odors, as well as ultrafine particles in form of suspended particulate matter level. So the technology which we use, we provide solution in this form. It's a hybrid solution, and this hybrid solution is consisting of MERV14 filters on return side, recirculating side of an HVAC system, as well as plasma ionization we are using into the supply side of the HVAC system. So as I am just showing a quick chart over here, that contaminants versus the solution which we are providing. So it's like, I mean, whatever kind of contaminant, whether it is originating within inside the building or coming from outside to inside the building, we are basically taking care of all type of contaminant by using this hybrid solution. So going further, I mean, the active air purification part of this central air purification system is basically that we are using these plasma ionization technology. So these are the devices, these are the kind of equipments which we place into the throw of the duct, into the supply side of the duct, into the throw of the air, depending on the CFM capacity of the HVAC system. And it's fairly easy to install these kinds of devices, these kinds of equipments. They do not bring any kind of pressure drop into the system, as well as they are completely suitable for a retrofit environment, as well as they are completely scalable, right from any kind of BRF system to air handling units. We have multiple types of HVAC system which can be integrated with the HVAC system so as to provide a source for central air purification. The technology is plasma. As we all know, the plasma is the fourth state of matter: solid, liquid, gases, and ionic gases. So we basically impart tiny amperage energy to the neutral oxygen molecule flowing into the air. So as the ions are created, positive ions are created, negative ions are created, and those ions basically, when we induce inside the building through the supply of the HVAC system. So let me just quick give a schematic for that. So here we are basically placing our system into the supply side, and these ions are created through these plasma system, and these ion gets induced inside the building, and once induced uniformly in millions of numbers in air as well as on surfaces, then these ions are going to eliminate these three contaminants, which are, as we discussed, the ultrafine particles, the solid particles. Basically, these ions impart electrostatic charge to these particles, and as the both polarity ions impart both kind of charges to the particles, particles start agglomerating, they start getting heavy, and as they become heavy, when they go back into the filtration side, into the return path of the HVAC system, they get arrested with the filtration system. So this is the first contaminant eliminated within the building from plasma ionization. This we are doing everything within inside the building, so we call it active air purification technology. Now, the second contaminant, harmful gases. Ions basically trigger a chemical reaction and break down their molecular structure. Example, any kind of odorous gas, for example, ammonia, when comes in contact with these ions, they break down into nitrogen and water vapor. So any type of alcohols, aldehydes, odors, volatile organic compound families, when comes in contact with the ions, they basically break down into less harmful components. The third contaminant, which is right now a major contaminant after this coronavirus pandemic. So these all microbials which live within the environment, and they are evolving rather. The evolution is happening as we are evolving, they are also evolving. We don't know what next. So to cater these type of harmful enemies, we basically, through this plasma system, what we are doing is these ions, once induced inside the environment, they directly attack on the infection triggering capability of these microbials, which is their protein structures. They pull the hydrogen out from these protein structures and basically render these microorganisms, their RNA, DNA into the space, which is harmless, as these proteins are responsible for causing infection inside the body. So this is how basically we are eliminating all kind of contaminants from the space. We have successfully tested our all equipments globally with various ranges of these microbials, volatile organic compounds, smoke, smog, ultrafine particles. And these are some of the reports, which global reports are available. We have tested the equipments on Omicron variant. We have tested the equipment on our equipments on other SARS-CoV variants, swine flu, common bacteria viruses like E. coli, Staph aureus. And these are some of the test report in some simulated environments also, which we have tested. So enough evidences are there, and enough substantial testing documents are available with us to prove the efficacy of the system. Now, as you can see in a nutshell, basically what we are doing through this plasma is basically we are making the particle size heavy so that they can get arrested within the filtration system. We break down the harmful gases present inside the occupied space. We break down the microbials present inside the space. So I can also say that we are providing the technology which is basically does not produce any kind of harmful byproduct, specifically in form of ozone. So all our equipments are UL 2998 certified, which is certification from UL for zero ozone, and so all safety and compliances we are following. So as I said, it's a hybrid air purification system. The second part is basically inclusion of all these MERV-14 filtration levels so as to increase the efficiency and as to arrest all kind of particulate matter entering inside the building from outside to within the building. So this is basically, we are a solution provider. Other I can say, I mean, this is how we design the solutions. We place filtrations to their effective place where they can best perform in terms of creating a defense or creating a restriction for all these harmful particles to enter inside the building. We place UV lights to clean the coils. We place plasma ionization so that a natural bioclimate is created within the occupied environment, and that can eliminate all the pollutants which are originating within the building, inside the building. We do air quality monitoring, and so as to show that how much improvement we have brought inside the environment after incorporating this complete solution. So this is I mean, like is monitoring part we are doing. We are into the process of developing a IoT based self-sustainable product, through which I mean we are basically targeting to eliminate all kind of consumables as well as maintenance type of requirements, type of loads from the end client. So this was the product line, as well as this is our process. Basically, whenever we start our work from day zero onwards, before that, from day zero onwards, we place our solution. But before day zero, we basically flush the air of the new building so as to remove all type of heavy contaminants which left because of any constructional activity or HVAC activity, so that from day zero onwards, whatever solution we have placed can perform on their optimized strength. These are some of our satisfied client, and from there onwards, I mean, I would say thank you very much for listening me and our technology. Thank you.
Thank you very much, sir. Thank you very much, and sharing the knowledge with us. And if you have any queries, you can directly contact Gaurav sir in the given number. Can you please share again, sir, your numbers and email ID in the screen?
Sure.
Yeah, so this is the number. You can directly contact, you can email to IntelliGreen. And once again, we are thankful to IntelliGreen Technologies to supporting this workshop and sharing the knowledge as well in front of us and for all the audience. So thank you very much.
Thank you.
Further, I request Waliullah Sidki sir, our program chair, to introduce today's speaker, Murlikan sir. Although Murlikan sir is well known and there is no need for introduction, but this is the SOP we follow. So I further request Waliullah Sidki sir to proceed from here with the introduction of Murlikan sir. Over to you, sir.
Yeah, thank you, Mr. Tapas. Thank you for giving me the opportunity to introduce Mr. E.R. Murlikan. And I would also like to welcome all the participants of the show, our fellow ISHRAE engineers who are participating in this great knowledge session. Our sponsor today, the sponsor of this workshop, the comprehensive indoor air quality solution provider, IntelliGreen Technologies, and Mr. Gaurav Chandilia, Mr. Vikas Jha, and their team for being part of this workshop today. And I'd also like to welcome all other participants, including our secretariat team, who does all the efforts to make such workshops and knowledge sessions happen. So today's coming to today's half-day workshop, which is being the speaker of the day is Mr. E.R. Murli Kant, and he is a well-known figure in the consulting fraternity, in the ISHRAE and all the field in our ISHRAE areas. So we are today discussing in this workshop on the piping distribution, piping selection, and the friction loss, especially in the chilled water system. And Mr. Mullikant today will be discussing about the parallel pumping, open loop piping, multi-story, how the multi-story piping can be done, especially in the chilled water circuit, in the condenser water circuit, how the primary secondary system can be designed, pump selection and power saving, how we can, the optimum pump selection can be done. And the other topics today which will be covering will be series pumping, closed loop piping, and friction loss, especially the friction loss, which is very important, especially in designing the pumps, because if the friction loss is not taken properly, then the pump sizes vary. That is a this is a difficulty. We especially commission the system. So as I told you, Mr. E.R. Murlikant, he is a consulting engineer and is a proprietor of MK Services in Chennai. So whereas he needs no introduction, but I would like to uh, tell a brief bio about him. Mr. Murlikant is a mechanical engineer and he has more than 35 years of experience. Presently working as a freelance consultant, providing consulting service in HVAC, fire protection system, storage tanks, utility and chemical process piping system. He is associated with some of the leading architects and MEP consultants in Chennai, mainly for clean room and hospital jobs. His core area is HVAC for clean room design, low relative humidity systems requiring lower than 15% relative humidity process, flue gas streams, and integration of HVAC system with fire protection system. He has been working with different industries in the past 35 years, and he is well known in the circuit. So we are instead of giving much further detail, I would like, in fact, I would request him to start the workshop. Thank you, everybody, and kindly make it a great session. And this is a big knowledge session, which everybody, I think, would like. Thanks a lot.
Good
So
afternoon.
over to Mr. Murlikant.
Yeah, thanks for the introduction. Good afternoon to all the participants. I'm really thankful to ISHRAE Delhi for giving the opportunity. In fact, I'm glad this is my fifth topic in the past 8 months and giving to ISHRAE Delhi on different topics. So really, it makes me more energetic to work with Delhi ISHRAE on various topics like this. Now, let me just directly go to the subject. Now, before going to the main thing, I would like to brief some points. That is, this in this particular session, we will not talk about the software being used for various piping and all. We'll be talking of only the main concerns while designing the piping and distribution the piping. Many doubts people are having in any time can definitely interrupt and ask the questions. One more thing I will have to tell you is we will be talking of basic science with some of engineering around to it, because science is the mother of all engineering. So in that way we start this program. Now these are various topics we'll be covering: basic terminology and units, pumping in parallel, pumping in series, closed loop piping, open loop piping, head loss, formula, and case study. 2 3 hours. These are the main things we'll be covering in this topic. I'm audible to all of you?
Yes, sir.
Okay. Pipe, it is a tubular hollow section made of metal or any synthetic material used for transport of liquid or gas across 2 or more locations. This is the basic definition of pipe as per glossary in the basic dictionary dictionaries. The selection of pipe material and cross section shall be to meet the flow. That is what flow you want in the system, what pressure, what temperature, what is the chemical property of the fluid, viscosity, density. These are the various minimum parameters that are to be taken into account while we are going with this I think some interruption is there, I believe.
Sir, is it not going in the slide from more? I mean,
Actually, suddenly there's a warning came, the site failed.
okay. So, should I try from my side,
Let me retry.
from my working station?
Let me try once again. Suddenly it was saying that it's coming now.
Not yet, sir.
It was saying my slide is showing that
Slide is visible, but I mean,
it's not coming in PowerPoint.
yeah, correct.
Suddenly it's disappeared.
So anyway, I'm
Coming now.
still in the same format.
Let me redo once again. So suddenly it was showing that it will be share screen. Something problem here. Right?
Please open your PPT, sir.
Zoom screen is disappearing. My visible is not.
Okay.
Zoom
I think I should share from my side then.
Zoom that screen is disappearing. Some network issue, I think.
Is it visible?
Yeah, it is. Suddenly Zoom screen disappeared. Now it's coming. Disappeared. Now it's coming.
So this is the second slide.
Yeah. 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 I can go to next slide, please. From here, okay, this okay. Yeah. Selection of pipe material and cross section shall be to meet the flow, pressure, temperature, chemical property of the fluid, viscosity, and density. These are major points we should take into consideration. However, for air conditioning application, chemical property is generally null and void because mostly we use either air, water or glycol solutions only, which is non-corrosive. Okay. Now, what are the units required to evaluate the piping? Flow meter cube per hour, or LPM, or GPM, or CFM, or kg per hour. Pressure, bar, kg per centimeter square, PSI, meter water column, millimeter of mercury, temperature, density, that is grams per cc, or kg meter cube, pound per cubic feet, dynamic viscosity, kinetic viscosity. Now, we should very important, we should know the different kinetic viscosity is equal to dynamic viscosity divided by density. Because in some formula it says dynamic viscosity and some formula it says kinetic viscosity. Unless we know the relation upon these two, we'll not be able to choose the correct units and the calculations all will go wrong. So we should know this difference between the two units. Okay, so let me go next step, please. Viscosity is a measure of the resistance of fluid to deform under shear stress. Okay, that is when you in science lab you might have seen you have taken some oil and put some ball bearing balls which slowly go down. If you recollect that experiment, okay, how fast the ball will go down, you can recollect. Dynamic viscosity is defined as the tangential force per unit area needed to move the fluid one horizontal plane with respect to other plane with unit velocity while the fluid's molecules maintain a unit distance apart. So these are all definitions. I just want to refresh in your science knowledge, but the terminology is very important. Units are important. Unless you know the units, you cannot get the correct calculations. Kinetic viscosity of fluid is the ratio of viscosity of the fluid to the density. Mathematically expressed as n is equal to m by p, where n is the kinetic viscosity, m is the dynamic viscosity, and is the density. Next slide, please. Viscosity of fluid is inversely proportional to the temperature. Especially why we want to stress on this little point is if we are using a thermic fluid heater, which is having a hot oil being circulated in systems up to 300 degrees centigrade or so. The same oil, when you have start from scratch, that is from ambient to 30 degrees, and so it will be highly viscous and dense. So it needs time to initial heat before coming to circulation. So that is very important when you have the pump selection for hot oils. This plays a very, very important role. In chilled water, it doesn't scatter much, whereas in chilled brine, if you're using minus 60 brine or minus 40 brine, there also it has to be carefully addressed because the circulation rate is different and the velocity, everything will vary based on the temperature. Again, we know density of fluid inversely proportional to temperature. When temperature rises, density decreases. When temperature lowers, density increases. So when selecting pumping and piping, temperature of media is also important since this has a direct effect on the pumping motor energy. So people should know the parameters. As long as in the ambient range of 30 degrees centigrade or so, there is not much significant effect. But when you go to higher temperature of 100 degrees centigrade or 150 degrees centigrade like that, there will be vapor accumulation also. So all this thing comes into calculations. Next slide, please. Pumping in parallel. Multiple pumps combined to have common suction and common discharge is termed parallel pumping. We'll show the pictures in next coming slide. In parallel pumping, total flow system is cumulative flow of all the pumps. The head discharge pressure shall be same irrespective of the individual pump flow. In this case, important to select all the pumps with same head. If pumps with different heads are combined, the net head can be achieved maybe little more than the pump with less head and less than the highest head of the pump selected. So in next page, you can go see the pictures. Next, please. Pumping in parallel. So we got a suction manifold, 270 metric cube per hour. We got different pumps, 50, 70, 90, 60 metric cube per hour. All the head is same. So cumulatively, we are getting mathematical total 270 cubic meter per hour. Variable flow of each pump and head is same. This is pumping in parallel. So it's mathematical total of all the flow of all the pumps, but head will remain the same. Now in the second comparison, flow is by and large same, but head is different. One is 20, one is 25, one is 30, and one is again 20. So net head discharge available somewhere between the lowest and the highest. That is ever 20 is approximately the net head available in the pump. So when you are expanding facilities, generally what happens is you having one building 1, building 2, building 3 like that. Initially they buy pumps for building 1, then for building 2, chiller everything in the same location and go for building 3. Now the distance between the chiller room to the building 3 is increasing. So what will happen is you cannot have the same pump head for building 1 and building 3 because the travel is very long. So in that case, what people will do, they will go for the higher head. So this is what I represented here, 20, 25, 30, 20. Assuming one building is the longest point, which requires higher friction loss, there we go for a 30-meter head to ascertain that water is reachable at the farthest point and the highest point. So this is the mechanism used in pumping in parallel. So when you're going for a gradual expansion in phases of building multiple buildings, we should be very careful to evaluate what is the head required and what is the head available in the existing system. What happens is many people they ignore the fact of this variation in the distance. Suppose the earlier pump was say 50 meter cube, 20 meter head, and the other pump the plan needed 20 meter head, 70 meter cube. What happens is the 20-meter head may not be adequate to pump water to the farthest and longest point. So what will happen in that new building, because of the lesser head selected by the agency, there will be ineffective water circulation, ineffective flow. Then people start breaking head and somebody will say change this, and it goes, excess goes on, continues for a long time, and the problem is sorted out. So let us not get into such long discussions unwantedly. We should be clear about selecting the pumps right from the day one. Next slide, please. Pumping in applications. Multiple user points with less head, but the height of the building is limited to less than 13 meters. Suppose you're having a building of 80 meters or 90 meters from distillation column, the cooling water or chill water has to go to 40-meter height or 60-meter height like the petrochemicals, where that very heavy tall columns are there and the tallest point you have to get the water. In such cases, pumping parallel to some extent will not help unless the head is set up properly. Now, in this pumping in parallel, when your multiple buildings are there, suppose one building is not required or shut down or not required on a Sunday like that, it can be switched on and off to meet the demand. Best utilization without EFD, where frequent change in demand is possible, especially chemical process industries. Chemical process is what happens, you have one chill water generation source, which will be distributing water to multiple heat exchangers. So one heat exchanger may be in line, other may not be in line. So it will be very unplanned way they'll be moving the process. So there we have this facility of switching on of chiller on based on demand. Similar thing is HVAC is multiple capacity chiller. Suppose in the phase 1, phase 2, phase 3 going to different buildings. In one building you put 80 TR, then 90 TR, then 40 TR like that. This compression can help with parallel pumping. Next slide, please. Pumping in series. This is very, very tricky. Many people confuse the this different. Hello? Slide before, please. Before slide.
Yes, sir.
Before slide.
Achha. This one.
Multiple, yes, same, correct. Multiple pumps combined to before one minute. Your slip slide before. Next before.
This one, sir.
Next one. Multiple pumps combined to interconnected suction to discharge to get greater head with same flow. In series pumping, all the pumps shall have same flow with same or various head depending on the actual head required. Discharge of first pump shall be suction of second pump. Discharge second pump shall be suction of third pump and so on. It is similar to having pump with multi-stage impellers. In this case, it is important to set all the pumps the same flow. Next, please. This is how it indicates. The below indicates a pump in series. Now, the first pump suction is 40 meter cube per hour. Suction is almost 0 bar. Then it gives a 2 bar output pressure. It becomes input to the second pump P2. It gives a 4 bar output pressure and again input again 9 bar. So discharge throughout will be the same, but gradually pressure builds up and pump 1, 2, 3 like that. It's nothing but a booster. You can say somebody say booster also, but all one is same. Now, but in this case, all interlock of all these pumps is very, very important. If suppose pump 1 or 2 or 3 trips for any reason, there will be severe head loss in the system. What will happen is the last machine which is getting this setting of water can trip or result in product failures like that. This is very rarely used in its application except for some multi-story buildings like say 30-story, 40-story like that, where we have a building height of cumulative height of say around 980 meters or so. It's very difficult to pump water to the tallest point. There are ways and means to address this, but for now the method is to have pumping in series. Next, please. Next, please. Hello. Hello. Next, please. Yeah. I think there's some problem with the video here. Some video here.
Yes, sir.
Some problem with the video. It's not image is not clear. It's some garbled like that. Can you please go back once again? Some problem with the video. Please go back once again. Forward now. Okay, now it's visible now. Now closed loop circuit system. Very commonly used for this set of chilled water, chilled brine, hot water, thermic fluid, etc. Major advantages: very less pressure drop, no need for hot well, cold well systems, no major water system except leaks from valve, gland, pump, mechanical seal. So generally we have multiple types of loops. One is closed loop, open loop, semi-open loop. We have got primary, secondary, different combination are being used for circulation in the utilities. So we can compare one by one. Limitations. Water makeup shall be planned suitably to overcome the line resistance, especially in multi-story buildings. When total water is drained out for attending repairs, refill of water is very, very difficult. Suppose you are having a 30-floor high building and you have to drain out the water for some repair like that. In that case, pumping the water to the topmost point is very, very difficult unless the head and all is set up properly. But closed loop system has got its own advantage in many ways. We'll come to that in the coming videos. Next, please. This is the few types of closed loop systems. One is without tank, one is with tank. In this first case, you have got a chiller, you have got a pump, and it's going all into the HU and coming back to the chiller. There is no intermediate tank. This is a closed loop without tank. And this one is with tank. In this only thing should be carefully taken is that the tank shall have no vent or drain. Because there is a vent or drain, it should be ensured it is neatly plugged or put a blind flange so that there is no leakage system. The advantage of closed loop with tank is, as I told you a few minutes back, after shutdown, when all water is being drained out of the system, will be advantages. This is we put the water in the tank and circulate, then entire thing will be easily completed. Whereas in the first one, it's very difficult to remove the air. In this, you can remove the air with the venting. After the purging, everything is over, you close the vent and total system remains sealed without any leakage. So this is one system which is followed in most of the chemical industries where multiple users are being used simultaneously, where the flow can be erratic, consumption can be erratic, very unplanned way. So second system is very favorable in such applications. Whereas the first system is mostly dedicated to HVAC system where you have defined load throughout the day. In the second system, you don't have a defined load throughout the day because of the nature of usage in the particular point. Next, please. This is the comparison between the two. Water loss negligible except for wall and pump leaks. With tank, as I told you, if the drain and vents are not leak tight, then probably there will be excessive loss in the system. Makeup water shall be given pump suction manifold. Tank shall be kept in pump manifold and makeup water to be given the tank. Working space, inertial space required, inertial space required for tank. Pressure rating not applicable because the pipe itself is a pressure rated pipe. Here the tank shall be suited, be designed to meet system pressure, otherwise it can develop cracks of excessive pressure. Vent and air trap, as I told you, very difficult to vent out air after long shutdowns, especially in high-rise jobs. Because you have to somebody go stop and keep on seeing whether the air is removed or some trap is there or not. Whereas in this, the tank acts as a good thing to wet out most of the air. Next, please. So open loop is other type. Very commonly for circulation, cooling water, chilled water, hot water system, the single tank. Chilled water tank with primary and secondary circuits. Any cooling tower basically is open loop circuit only because the water from the tower sump goes to the heat exchangers or condensers and comes and falls back into the cooling tower sump. So there is a need to have proper head design in the system to ensure the water is taken to the topmost point easily. Major advantage is the tank as energy bank, mainly for large capacity systems. Easy delivery and replacement of water. After every start and restart, say you are having a shift of two shift operation. Night the man has to switch off and morning he has to come and switch on. Whatever the energy is stored in the tank will be good enough to start the early morning. And that time chiller will not run in full load because already there is some energy hold in the tank. That's energy tank. Limitations. Tank water shall be maintained properly to prevent suction starvation in the pump. Tank offers possible when power changeover if tank capacity is not adequate. Here is a very important thing. Suppose you are having a 5 kL of tank, okay, and header volume is more than 5 kL. Suddenly there is a power failure. The pump will stop and all the water from the return header will fall into the tank and result in overflow. When you restart the system, there will be sudden water drop. The system, entire empty pipe will be filled once again. Again, you have to add extra water. When you add extra water, what will happen? The delta of water increases. So, chiller load increases. So, the tank capacity has to be adequately sized, keeping in mind the maximum possible collection of water from the return header, especially when there is a power failure. But however, if the tank is kept on the roof, say a 5-story building is there, and you're having a chiller and a tank on the roof, there your overflow loss is very, as I would say, negligible. Whereas the same 5-story building, if your tank is in the ground floor and with the power trip, the entire return vertical head of the total pipeline, water will come and fall into the tank into overflow tank. So this is where the importance plays while selecting or deciding the open loop system. A single tank, okay, chiller, AHU, and this was the return line I was telling you. Suppose this is in the ground floor, what will happen is the entire volume will come and fall here. If it is in the top floor, the return volume will be less. Okay, here the chiller, just one small difference is here is the warm water from the tank goes to chiller. Here, the air tube comes to chiller, the tank, and cold water. So can hello.
Hello.
Yeah, some interruption suddenly. I don't know why.
Okay.
Suddenly, some problem is coming on the way. PP is not visible. Yeah, now it's visible. Okay, now correct. Next is your open loop with cooling tower. Here you were selling few minutes back about cooling tower. The pump from here is going to heat exchanger and coming in falling into cooling tower. Generally, cooling tower in typical plants are kept in the ground floor. Very often we see the water overflow because the heat exchanger is kept at maybe 20 meter, 30 meter high from the building, from the ground. So what happens when the power trips, entire water comes and pours the cooling water leads to overflow. So many things are common, which is only we have to adequately size the return gel or pipe volume. Next, please. Now here you got open loop with primary and secondary circuit. Okay. In this chiller side, there is no tank. It is a closed circuit. Whereas in the AHU side is a open circuit with a small tank in between. So these things again, right side of the picture is used when you have very long pipeline travel. Whereas the chiller needs a very compact low piping within the building. So it is a small loop, whereas here is a big loop. So these are all different options. Here you have only one heat exchanger is there, which will do the cooling of the system. Chiller will pass the heat exchanger, come to the chiller, and this heat exchanger other side will cool the water from the other side. Next please. Now this is a cold well, hot well conventionally used. Okay. From the chiller going to tank, from pump it is going to air to coming to hot water tank and pump. So this is also another way. Why I want to touch all these various systems, because this has the important role to play when you're working on the friction loss of the piping. We should know the alignment, we should know the system, what is being conceived and asked by the end user, either primary or secondary or only primary or a closed loop or open loop. Unless we know the exact requirements by the client, just designing system many times will lead to very complicated, especially after commissioning. People will be breaking their head, find out why we're not getting water at the right place, right time. Next please. Now, some comparison, small comparison, hold up tank, closed loop optional, but if she given should be vent free and leak free, open loop should be provided. Hold up tank as energy pan, yes. If it is given, it gives a energy pan, whereas in this it's a good energy pan. Either way, hold up tank is useful. Next please. Next please, yeah. Of system airlock removal after water refill difficult since is to be done multiple times at different locations. Simpler since tank venting is mostly adequate. Space utilization, yes, here is space is saved, here is space required. Piping is less, is more. Water overflow is completely sealed, so no overflow. It is possible whenever some power is interruption is there. In multi-story application, a minimum required, more head required. This is a very interesting thing. When we go to the topic on the multi-stage, multi-story building, you will find this very interesting in closed loop functioning. I think we are now taking the major part. From now on, we'll go to the heart of the system, that is the calculations or things. Next, please. Now, in piping, mainly two concepts apply. One is Pascal's law and head law in fluid pumping. Now, Pascal's law says when fluid at rest, the pressure applied at one point is distributed equally to all parts of the liquid, irrespective of size and shape of the container. This has important role to play while understanding the hydraulics of the pumping system. We will go in slightly in depth when we go down the other pages. From this, we derive law of energy, apply on the fluid potential energies mgh, where mass is equal to m, g is action in gravity, h height. Okay, here will be head. Now, kinetic energy is equal to half m squared. So, where mass is equal to mass, v is equal to fluid velocity. Equating the potential, we get head is equal to v squared by 2g. Now, this is the basic theory applied for all hydraulic calculations. What head is required, it depends on the v, that is velocity of the fluid. What is this velocity, 1 meter per second or 2 meters per second, whatever the velocity you're considering. So, you will find in the coming pages that the moment to increase the v, that is velocity, the loss goes very high because square root goes in the power of 2. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So increase velocity goes square times. This is a basic thing we are applying in all the hydraulic velocity calculations. Next page, please. Next page, please. Yeah. Now, head is equal to v square by 2g. Yes, I told you. Maximum point required to pump, that is the tallest point of pumping system. The friction loss, equivalent loss in system that consumes energy loss and also does not allow the liquid to reach the tallest point. So when V is high, velocity is high, the friction loss goes high, and the required head system drops drastically. Why this happened? Input energy is consumed because of friction in the horizontal plane, resistance in walls, bent steels, etc., across the equipment through which the liquid flows. The balance energy available after these losses is not adequate to pump liquid to the tolerance point. Here is a very, very important point why we have to stress again on V, that is velocity. Again, repeating once again, input energy is consumed because of friction in the system, distance in walls, bends, etc., across the equipment through which liquid flows. So the net energy available may not be adequate for the water to reach the farthest and tallest point. Next please. Next please, yeah. When pumping the fluid, the below factors are considered for adequate pipe sizing to ensure less head loss, less pumping energy, especially in multiple distributions. Minimum and maximum flow permissible across each machine. Data from machine supply can be worked out based on heat load from the machine, etc. Pressure drop across the machine. Again, supplier shall give the MOC of the pipe, maximum tied to the point of location for the machine room, pumping source, and fluid velocity. Again, the velocity is the culprit everywhere. Next, please. Now, head loss due to friction is given by the equation dP is equal to F or V square by L by 2D. That is pressure drop in Pascal, friction factor, density of the fluid, velocity, pipe length, and pipe dia. Next, please. Friction characteristic by the formula, the E reference number, dia and pipe Reynolds number. F is equal to 0.25 divided by log 10 of this E by D. This is a big formula. Okay. Now Reynolds number can be equal to formula. Again, R is equal to RBD by M. That is density, velocity, inside pipe layer, and dynamic viscosity. In the starting, I told you there's a difference between the viscosity, is dynamic viscosity and kinematic viscosity. So when you choose the number, you should very, very carefully which unit you are following, dynamic or kinematic. If you put wrong notion, the entire result will go wrong. So this particular formula is as per dynamic viscosity only. Okay, next please. Now all the three. So now just imagine what is the result of what work. Okay. Now dp, what we said is spirit pressure. It is a correlation of F, that is fission factor, and fission factor is correlation of Reynolds number. So many people use one ISHRAE chart or ISHRAE a small chart which says this much 0.1 feet per feet or 0.2 feet per feet, something they have a printed graph. From that we interpret and say go for 2-inch pipe or 3-inch pipe or 4-inch pipe. Are we right in that? Are we not right in that? To what extent we agree or disagree is always a debatable topic, because many of us are not aware the importance of these three functions. Roughly, many of the people habitually using the ISHRAE. I'm not saying it's wrong. I'm only saying is we can use that, but we should do some little homework using this formula to evaluate what is the pipe size required and what is the friction loss from the system. Unless we do these proper calculations, many of our pipe selections or pump selections, everything goes for a different disturbance here and there. So repeating again, first I showed you the three separate formula. Now I have put in the common picture which defines you the relationship of all the three. So pressure drop has got a relation with the friction factor, which is again as a relation with the Reynolds number. So unless we have to go from the reverse. We should know what is the Reynolds number first in the system. Then we have to, from that we have to work out the friction loss. For roughness number you get from the piping manual as per API. Okay, which is 2-inch pipe or 3-inch pipe has got so much roughness is there. It will be the table is there. From that table you can derive the roughness number, and Reynolds number can be worked out, and finally put all the things to get the friction loss in the system. Next, please. Next, please. Yeah. Yeah. Now some concepts in piping distribution. See, one small case study I'm telling here. Closed soup is AHUs are kept on roof. The conditioned space is 5 meter and chiller and pump room. The actual water level shall be inverted U2 millimeter. Hence, the vertical pumping here should not be a main concern except for initial filling only. Initial filling system shall be used by some alternate resources. The two buildings, here is a pump room, 20 meter apart, they are having the AC room. So how it behaves, I tell you. Next page, please. So this is the picture. It is actually we have says U2 manometer. Now we discussed about Pascal's law. Okay. Now the pressure applied at one point will be used travel is throughout the system. Now this is the left side is the AC room, and right side is the pump room. Now entire line is closed loop system, closely sealed and filled. Now even if you apply small pressure at one point, automatically the system water will start circulating. For example, you got a hydraulic this vehicle repair station where the car is lifted. You got a small piston where the piston pumps the fluid, and the 1000 kg car is lifted by hydraulic jack. Okay, so pressure applied one point, small piston gives lift to a big car. Same way here, the U2 manipulator, core is sealed. If you apply some pressure in the pump, it automatically will push the water entire circle. So here, the initial filling shall not define the head required the pump selection. It's very, very important. Now, pump energy requires desired peak flow and overcome the maximum friction loss in the systems. Okay, next please. How we choose a pump? It is important to know a single pump is certain. Some major elements are flow, head, density, viscosity, wave pressure, type of suction. We are all aware of this. Next. This is a generally how the pump curve is look like. When you can count any pump supplier, KSB, Gunfast, whatever, it will be universally curve given by the pump supplier. The blue one line defines the duty point for which are selecting the pump. Okay, and this small inclined one is pump curve, and this what you call this some inverted curve type. It is the power of the pump. So this is the simple pump curve anybody gives. We should know how to work on this. Next point, please. The next point, please. Yeah. Now, how the pump power is required? Calculated. It is pump shaft power. Density. Q is the pump flow. How much is the flow? R is the density. G is acceleration due to gravity. Head is the watch head you want, and efficiency. Generally, pump efficiency varies from 65 to 70%. But using the software, the pump person can tell you for the selected model what will be the efficiency he will be giving to us. But roughly, this is the formula. So we can arrive at what is the pump shaft. Pump shaft power different, motor power is different. Okay, suppose pump shaft power is say 10.3 kilowatt, you go for 11 kilowatt motor or 15 kilowatt motor next size. But irrespective, pump will take that much kilowatt only, how much it requires. If it is taking more kilowatt, the water will trip. That's it. Next step. Next point, please. Now, if you give some data to the pump supplier, he will give you some of the models. Okay, pump manufacturer say here is some CC 150 200 or some model will tell you. He will sell the pump people dia. He will tell you what pump RPM he looks for as per the available current catalog with him. Calculate the pump efficiency software and recommends the motor. Now, for any application, impeller dia and pump RPM are the crucial things to understand how they behave. What people do is any pump person, suppose you tell him on flow and head, he'll always give you the recommended impeller size for the certain pump. So once you purchase the pump with impeller, you cannot change the impeller. It will be lifelong same impeller. That has got a crucial role to play when you practically revisit the power required in the site. Many occasions, head is overcertain, resulting in poor performance. Go next slide, please. Now, here is the comparison. Now, a pump was selected for 30 meter cube per hour at 20 meter head based on some assumptions. After commissioning, we found the energy is taking very high. The actual building height is 5 meter and the actual head measured 8 meter. After friction loss and all, 8 meter only head is required. But we have selected a pump for 20 meter head. So this dotted one is actual performance. So when the head is falling down, the flow goes to the right side of the curve. The blue one was the what was selected, but after this, what happens? Because this change in actual site conditions, the head has fallen down, whereas the flow has gone to the right side. Next, please. Here was the comparison. The actual motor amp was measured, actual head was measured, and flow was measured with the flow meter. Now we noted this, and you reworked on this. What is the efficiency pump? See, when you measure the amps, we know what will be the kilowatt of the pump. So that we got it. So the design was to get 2.6 BKW. Okay. Whereas because of this variation and shifting in parameters, actual parameters, when you measure the flow and amp at the side, we know that instead of 30 meter cube, it's 70 meter head is giving the flow, and head is 8 meter only. So pump everything is fallen down and is taking 3.5 kilowatt. That is 0.9 kilowatts is taking extra energy. Now, as I told you a few minutes back, the pump man will always give you the impeller RPM and the impeller diameter. So pump is ordered, pump has come with a fixed RPM and a fixed impeller dia. We cannot do anything with that. Why there is no energy saving? Because of this. Instead of 2.6 kilowatt, it is 3.5 kilowatt it is taking. And giving the much higher flow. When you give higher flow, it doesn't give proper delta T in chiller also. So what will happen? Instead of 30 meter cube per chiller, you 70 meter chiller will not give proper delta T. All these things are interrelated issues. Okay, so that's why I told you in the previous few slides that V squared, that is velocity, is very important, and head is very important. Unless we know the head is what actually required, and we are blindly over designing, this is where we usually land up. Next, please. Next, please, yeah. Now, head loss due to velocity, formula, pressure drop, friction further discussed. Applying formula, some interesting results. 5 day of various sizes, velocity same in all sizes, length. Now, I'll show you an Excel sheet from my thing where we'll have a comparison. I'll just show it. Can you please for a while close this, please? Thank you. I'll show Excel sheet to you so that you can see the difference. Excel sheet visible?
Yes, sir.
Again, is Zoom is getting disappear on that. I don't know what is happening here. Going on here.
Sir, it was visible Excel set.
No, I say the Excel sheet I am not able to see it. That's the thing here. You are seeing this sheet here?
Yes, sir.
This one, roll 1, roll 2, that you are seeing that Excel sheet?
Yes, sir. Fine.
Roll 1, roll 2. Okay. Now, here is right. Last one is the friction loss. Okay. Now, 18 meter cube per hour is the flow. This now this velocity I am changing here. Okay, I am putting say 2.5 meter per second. Okay, rest for a while. I'm just deleting so you can concentrate on only one value. So 2.5 meter per second I put here. The friction loss is how much? 3.6 meter. Length is 35 meter. Again, I'm putting back again. I'm putting 1.2. Okay. Friction loss. Pipe length is same here. Okay. Pipe length is same here. Now it's come to 0.363 meter loss. Okay, I'm putting 2.5 meter per second. Okay. Now, pipe size instead of it's come to 50 dia. Now this is the loss, 3.6 meter the loss. So I told you V squared by 2G, correct? So when I am changing this one, what you call velocity meter per second, for the same pipeline, 30 meter length, the velocity 3.6 meter per second. Now let me show you one more comparison here. 18 meter cube per hour, I am putting here 1.5 meter per second. Okay, it comes 65 mm pipe, I put here 65 mm dia pipe. Okay, and here I am putting this length as a 90 meter. Okay, now for 30 meter length at 2.5 meter per second, the 3 meter is the loss. Okay, but same flow 1.5 meter per second, the pipe is situated here, 90 meter length or 2.7 meter. So this is how quickly it behaves. Again, 33 meter here length is only 1 meter length loss. So that's why it is very, very important to understand the importance of friction, velocity, because it goes V squared. Reynolds number also just varying each time. If I change this to 2, Reynolds number is varying. When you change this to 1.8, it's varying. So it has got a correlation with everyone. So just like that, we cannot say, okay, blindly go for this or that. Okay, so this is what I just wanted to make importance. So when you're selecting a piping, what is the length of pipe, what is MOC of pipe, what is the velocity you are trying to keep, what is the dia you are considering, everything has got a interrelation to select the pumping head suitably. Yeah, let's go to the PowerPoint, sir, please. Let's go to PowerPoint, please. Yeah. So the same velocity and length, the friction loss is more in similar dia pipes and less in larger dia pipes. This is what I was just trying to explain in the calculation now. Next, please. Yeah. Here, the same thing I put it here now. Different pipe dia, 15 mm dia, pipe length is constant here, velocity is constant here. Okay, because the velocity is 1.6 for half inch pipe, so getting a 2.606 meter loss. At 25 dia, generally people again are going back to previous what we discussed. People refer a ISHRAE graph saying go for half inch pipe or 1 inch pipe or 2 inch pipe like that. Which is many times, especially smaller pipe there, it's not the correct way because the same velocity 1.6 feet per second. Okay, what is the loss we are getting for 20 meter pipe length? So this is how actually it behaves here. Just by looking the ISHRAE graph, if somebody is deciding the pipe size without going through these facts, naturally the pump selection head will be more than required, which will result in power loss. Okay, next slide, please. Now, I was just talking about this multi-story building. Let us say one 4-story building is here. In this first two left side, pump chiller in the ground floor. In the right side, we are kept in the roof. Now, either way, it is a closed loop U-tube manometer because the entire water is sealed with water. The energy required for this total pumping is only to overcome the horizontal resistance and not vertical resistance because the U-tube manometer by gravity from top to bottom, water will travel on its own. Okay, and we need only little energy to push it across this various units. Suppose you kept in the roof against inverted, it comes like this. So this is a simple comparison. What people generally do, they take the height of the building to consider the pump heading. Many times it's not required. Many times you just work out on this requirement of the self weight of water and the horizontal loss that is adequate for the system. Next, please. Yeah. Multi-story chiller in ground floor. Option 2, chiller on roof. Okay, both are closed systems. Inverter duty manometer, this is normal duty manometer. Pump energy for water flow top to bottom negligible since it is easily by gravity. Entire pipe tank full of water, leak tight. A slight push on one side will automatically push all the fluid, which discusses of Pascal's law. One small push on one side will transfer all the water throughout the system easily. In this case, head required is overcoming the horizontal loss in the pipeline and loss through the walls, bends, coils, etc. No separate head required for total building head for normal circulation. Okay, next. Next please, yeah. Now energy saving. Now here is very interesting. Now what happens is many times these AHUs will not be running simultaneously. Some may be running for 2 hours or 8 hours or 6 hours, depending all those things. So to carefully observe this sketch, the right side I have put a red line. That is what I am doing is I am short circuiting the supply and return line together in each floor at end of the header. What does it mean? Suppose some of the AHUs are off, so there will be no return coming from the system. Okay, because only supply will be there, return will be stopped. There will be some starvation in this system. And suddenly when you switch on the AHU which is off for maybe 8 or 10 hours, there will be sudden jerk in the temperature band. So by putting this in connection to this loop, what happens is there will be no starvation. All the lines will always be full. Then there will be better thermal equilibrium maintained in the systems. There is no unwanted backlash. In this previous one, there will be dead main flange, so there will be water will be stagnant at the farthest point. By intersecuting this, we will be having no dead length, and all the water will be in equilibrium. If supply and return line are load at each end of header, in part load, return back to the pump is low. This creates backlash in the system. By connecting supply and return, there is no backlash. The thermal balance also better since supply and return are getting fixed in each floor. Next, please. Now, a multi-story commercial building with 28 floors. I don't know this is visible, how much I don't know. They're all only for AHU application only. Roughly each floor had a 18-meter pipeline for each AHU. So these are the various things. Now the total head loss in the pipeline almost 10 meter. Okay, number of falls approximate 200 numbers equivalent to this much, and adding all to almost 32 meter is the head loss. Okay, expert system loss is 46 meter. That is 4 bar is the head loss. Okay, AHU coils, all this is put together. This is the actually head loss expected system. So expand please. The actual design was like this. A small plot diagram. We got AHU up to 27 floors. Okay, return coming to primary pump, chiller, some TR, secondary pump, 50 meter head is going like this, and there's a decoupler for short circuiting the cold water sector. Okay, now what actually we observed in this is very interesting. Next slide, please. Now, 27 floors are there. If you go from top to bottom, okay, and chiller is kept on the roof. Okay, this is the gravity head. At 17th floor, they are getting 40 meter head. It is coming from reverse. Okay, zero gravity. So 40 meter is the head we are getting, and 14th floor 50 meter, and 12th floor 60 meter, and 9th floor 70 meter. Just gradually see from here it is increasing. Self weight of water by gravity. Return is by gravity. So self weight of water is increasing gradually. So and bottommost is the highest pressure. Go to next part. And for ground floor you got almost 104 meters, 10 bar pressure. Okay, so go back again. No, this table before. Okay, back. reverse, back. Back. Stop. See, 17th floor is 4 bar pressure, 14th is 5 bar pressure, 12th is 6 bar pressure, and 9th is 7 bar pressure. Pressure gradually increasing. Okay, and the go next, please. At a bottom most, you got a 10 bar pressure. Now, generally, all AHU coils are designed for 6 bar pressure, working pressure maximum. And if you give 10 bar pressure, you can imagine what will be the life of the AHU coil. Within a span of 1.5 years also, it will get puncture. Similarly, for chiller evaporator also. This can lead to early leakage of coils. Next, please. Now, this is the pictorial representation. We are getting 10 bar pressure at chiller. All flows put together. 10 bar. Will each chiller man accept this pressure? Nobody will accept because evaporator is not designed for 6 bar pressure. If you count 10 bar pressure, then you have to go for a higher cost. Everything will be higher. Now, how did we address this point? Next, please. Now, what we did is, where we identify the node where the high pressure is coming. So from here we have put a pressure relief valve, a small one is pressure relief valve. From pressure relief valve will come, okay, will go to primary circuit. And from here again another pressure relief valve circuit. This is to prevent the AHU from damage of high pressure. AHU coil, I mean to say. So we had identified the nodes, put some pressure relief valve, which will maintain the pressure below 5 bar or so at the edge coil, and rest of the water will bleed off. All bleeding waters will come to the primary pump. Pump is no issues. Now here it becomes as a, I told you the pumping in series because from here it is going here and going here. The pumping in series only. So we pump it, there is no tank, anything between. Now again, chiller will not, this pump is already this is a 20 meter head, already having 100 meter head here. So 12 bar something pressure going here is not good for a chiller. So we put another pressure relief valve which will bypass chiller and give you. So any given, there is no thermal disturbance because all this water getting mixed throughout all places. So thermal equilibrium is not disturbed. Okay, and pressure is by and large within the limits of the design parameters. Otherwise, what will happen? The AHU coil may fail or the chiller evaporator tube may fail. So this is one of the typical examples where we have to strictly identify when designing head for any pump. So next question, next please. Now, how it goes? Fourth floor is 5 numbers AHU. Another one, come to 3 wall 2 wall. A small study for putting 3 wall 2. They have got 4 floor building. Fourth floor is having this LAC working from this time working here, and 5 numbers are identical buildings only. And third floor State Bank of India and DPO. Second floor Max office and office. Third floor is hotel and spa and office. These are occupants in the various floors. All roughly identical capacities. Ground floor where chiller, pumps, electrical room, parking, etc. Chiller capacity is 300 APM. Here and pump capacity this much we are having. This is what we have a case study for a commercial building. Now, should we go for two-way wall or three-way? So, the client was knowing to understand what is the benefit of which wall to go and what is the probable saving energy because of going for a which wall type of wall. Okay. Now, this was again for a constant speed, not variable speed. Constant speed pumping. Okay, next please. See, in two-way wall, see 100% open, all water is going back, so there is no backlash. Partly open, so little backlash is there. Fully closed because no load, so more backlash. So incoming water will be there, where will it go? It will not go, it will be stagnant in the AHU cooling coil only. Again repeating, 100% open, all water going back, partly open, stuck up here and fully closed, no water going back. So pump is there is unwanted back pressure. Next, please. Now, what does 3 valve do? Again, 100% open, no issues. In 40% load, okay, 60% is going bypass. That means your supply water, return water are getting mixed. So your delta T is narrowed down, okay, and no backlash because no resistance here. And 70% open again. Delta T is low because of fixing 30% going back. 70% is the load, no backlash. Now 100% close. Delta IT will be same because water in water is going out. So no 100% water is going back, and your temperature also there is no increase in temperature unwantedly. So you are having a better energy saving. So whenever the water is partly open, there is always a mixing of this cold water and hot water across the coil. So it balances the thermal equilibrium. And 3 valve, if properly utilized in size and given proper automation, definitely it gives energy saving simply because of the delta T across chiller is narrowed down. So when delta T is high, the chiller power will be high. When delta T is low, the chiller power will be low. Yeah, next please. Now, comparison of the 100% load, valve fully open. In fact, 6 a.m. to 9 p.m. roughly 20% load only will be working except if you all edge valve close. Since we have all water return back to tank, you will not return full water tank. Water level may fall down in chilled water since tank is less. Now, when somebody switches on the air tube, what happens is there is a sudden jerk of water coming back to the tank or the return lane. So there will be sudden surge in the water level. If you're having a say, small tank, it can get to overflow unwantedly. So 3 valve, there is no such chance of overflow. All water is coming back safely and no issues. Next point, please. Again, 10 a.m. to 6 p.m. almost 100% it is all low. So again, same thing. Okay. So each wire is getting better mixing, better thermal equilibrium. And next page, yeah. So 40% load again. Delta T. Everywhere we can see the delta T plays the important role. 3 valve is very important in getting lower delta T in multiple systems like this because low delta T means less chiller energy. And next page. Again, Sunday holidays, little of occupancy. Most of things are closed. Maximum load is reduced, but you have got a better delta T. Next. Now here is where the pump performance. In partial load, only partial chilled water return to the chiller. Okay. In all loads, total water comes back to chiller because the two-way valve it restricts some of the water. So, suppose 100 liter per water has to go, and it is for 40% load. So 60% water will remain in the gauge coil. Only 40% will come out. So when multiple AHUs are running like this bar load, the frequent switch on and off, what will happen? There will be a starvation of water coming to the pump section, which may result in airlock and unwanted issues. Whereas in 3 valve, there is no starvation except for the little amount of hold up in the gauge coil. Rest every water comes back to the pump inlet. So either way, 3 valves, either in a part load or switching frequent switching on and off, it has a very good effect. Now pump load kilowatt maybe 0.3 or 0.4 kilowatt saving you may probably assume by putting VFD. But every delta T of chiller will take more energy. That's very important. Next page. Yeah. Now this is the conclusion. Gaurav Upadhyay's multi-floors and multiple building services benefit of for 3-way control valves. To make water required system is minimized. Water load due to delta T increase, pressure is minimized. On the other side, due to sudden load jerk, excess water return to tank is diverted. This for 3 12 comparison. Next, please, yeah. Now, this is a summary of discussions. We had parallel pumping, cumulative flow of multiple pumps and same head, and all pumps shall be of same head. Series pumping, nothing like a booster pump. So one pump will pass the water, other pump like that, it head goes on increasing. Piping, yeah, closed loop, open loop, we discussed. Pipe sizing, we discussed the importance of friction loss, the Reynolds number. Pump with same impeller dia, different all these we discussed. Now, I think I have given my learnings the best what I know, and let us go to QA, question and answer session. People can have any doubts, can directly question me.
Thank you very much, sir. Thanks for your great presentation. We have some questions in Q&A session. We'll take it one by one. Which is the better design related to open loop?
Open loop, see, I just told you, open loop, we have got say, 2 types of open loop. One is on the primary side only, one is on the primary secondary both or secondary side only. Primary means I'm on the chiller side, secondary means the AHU side. Now, if you're having a long travel of pipelines from plant room to the AHU system, I would prefer to have a double system. What is primary without tank for chiller, because chiller doesn't require much of makeup water very often. Okay, whereas the secondary side, where is going to the AHS other systems, better to go with a small tank suitable capacity, which will add energy bank. Plus, anybody drains water due to shutdown or something like that can be easily noticed and make up in the system. This is what whenever we discuss for open loop system. If there are certain cases, even the chiller also suppose have multiple chillers, 5 chillers. All the 5, I'm talking excluding standby. Excluding standby, you are having 5 chillers at different capacities. Depending on the demand, 3 may work or 2 may work or 4 may work, depending on the demand load. So in such cases, I would suggest you go for a open loop system, because whichever chiller suddenly goes for a start stop, accordingly the pump will go for a start stop. You will be able to monitor the water level. If required, you can add on water to make it better control. So it depends on the application, number of chillers, location of chilling plant, and the user plants. Open loop, both closed loop, both have got their own plus and minus. But in multi-story buildings, please limit to closed loop only.
Yeah. Moving to the next question. With respect to pump selection, horizontal or vertical, which should be the preferred?
See, if you have space constraint, vertical is the best. Okay, performance wise, both are good. Maintenance wise, vertical is less simpler compared to horizontal, because in horizontal pump, first is alignment is usually a issue. If you don't properly align them, first thing will be the mechanical seal to fail and the coupling will fail. Whereas in vertical beam, it is I will be directly coupled onto the motor. There is very remote possibility of misalignment. The life of vertical pump is much higher than comparatively normal because of many alignment issues. Yes, and space saving, yes, horizontal pump has got more space and vertical has got less space, but lifting mechanism, suppose you are getting a 30 HP, 40 HP bigger motor like that in a vertical pump, then you need to have a proper device to lift the motor from the position to go for a repair or whatever it is. If you don't have proper lifting mechanism, it will be headache. You have to do proper chain block or something. That's the only thing. Otherwise, performance wise, both are no issues.
What will be happen if we reduce the flow when the actual head is low at side?
See, that's what I told you. See, pump impeller dia and RPM are fixed based on what you select at the time of designing. Now, what happens is many people they select for higher head, and when they observe the head is very less, which increases the flow, they go for VFD. Okay. VFD has got its own limitations. See, if you say all motors are VFD compatible, VFD compatible doesn't mean you can lifelong run with 30 hertz or 40 hertz. What people usually do is they select the full RPM motor and forcibly run the motor at maybe 40 hertz or so for so number of days, a number of months. Now, all these motors are designed for a with fan cooling for a specified RPM. Okay, it's called TEFC motor. Suppose you are reducing the frequency, RPM will fall down. You may meet the pump head, but what will happen to the motor cooling? You not get adequate motor cooling. Number one. Number two is very, very important. By reducing the motor RPM, possibly to 40 hertz also, because of less cooling, motor overheating will increase, and the power factor will get changed. So if you're having one or two pumps, fine. If you're having 12 or 14 pumps, not only for pumps, for AHs, where you are putting VFD, your power factor in the system will go for a disturbances. So you always, and you have to, if you don't have proper capacitor bank of the power factor related to the issues, then you may see the ammeter of the motor and tell, okay, I'm saving this much amps in this motor. But in the overall factory scenario, if you take a power factor, you see it will be a huge loss. And we should always maintain power factor more than 0.9, close to infinity, close to 1. 1 is not possible, so 1.93, 0.94 like that. But many people, what they do, here is where they lose the energy unmotorly. They have multiple motors for AHU and pump with the VFD 30 kilowatt, 20 kilowatt like that. And power factor, they don't take proper evaluation, and they keep on paying heavy EB bills. You may see only the ampere of the motor for the pump or fan, but the demand of the factory will always be more than expected. Sanction demand is different. Suppose you're having a 1200 kVA demand, expect to run at 1100 kVA. It will now be 1100 to 1120, 130 like that. 20, 30 kVA extra you have to pay each month just because they're running with the VFD at 30 hertz or 40 hertz for a long time. Then next, please.
Is series pump is a good design?
Series pump is not good or bad, as long as you see if you're having the head, see, for example, low flow of 20 meter cube per hour and say 80 meter head, you don't get pump easily that category. Either you go for multi-stage pumps, that is one pump having multiple impellers, or go for a series pumps. Ultimately, your head is should matter.
How we decided we have requirements of secondary pumps in our system, where we selecting only primary and where we selecting both?
Yeah, that's what I told you. Secondary pump, suppose your transmission of filled water from generation source to the user point is very long, go for 1,000 meters or rather long, lengthy loop and multiple. There you have a secondary system which will have a possibility of using multiple units at the same time. Whereas if everything is in concealed in one small space, then secondary not required. Suppose there are only 4 floors, okay, how could be 3 edges per floor, then 12 edges. For 12 edges, not even secondary not required. Suppose you got 3 or 4 buildings, source of still water is safe. 3 or 4 buildings you have to cater, and multiple edges. Then better to go for secondary system.
So thank you, sir. The question that we have received in Q&A section is well taken, and I think it is well knowledgeable program under your guidance regarding the piping distribution, selections, and friction loss. Once again, thank you for IntelliGreen Technology to supporting this event and sponsoring this workshop. And of course, all the annual partners what we have right now are myself, Aeroplex, LP Aeroplex, KSB, Syscam, Advanced Valve, Marvex, and ISHRAE Parliament Poultry, KFlex, and Standard Affiliation, so supporting each and every event. And of course, this is a vast topic, and we can make a further program in this topic with you also again. So, any feedback from audience are always respectable, and we'll make the plan accordingly. Yeah.
I put my cell number in the side because the note.
Yeah.
The
Yeah.
chat box. I put my cell number because the note.
Okay. So cell number is there in chat box for Multikant sir. So you can directly contact to him further any queries related to this topic, or I think he's the master of many things. So you can take the guidance from him for another one as well. So I think we are at the end of the session. Any final? Before closing this, I request everybody who is a non-member here. Each and every webinar I request, and again I'm requesting you, one who is non-member here, they can easily join to Delhi chapter of ISHRAE by going our website or ISHRAE.in, that is the headquarter website, any website. Just you will have to select Delhi chapter of ISHRAE. There are nominal fees for the 3 years and 10 years. There are 2 options. Just fill up the form of your qualification and other details. After selecting the Delhi chapter of ISHRAE, and you will the member, and within a week or 15 days you will receive the documents from the headquarter as well. So very simple process is there, and you must know that we have abundant of program this year upcoming, like cricket, Vendconf, right, Pharma Fest, and many more. There will be opportunity to physical interactions. So we provide, ISHRAE is the main objective for ISHRAE, as we know, disseminating the knowledge. With this, we provide the platform to interact with the business community, consultant community, other office contractor, government officials are already regularly come in our programs. What we do, so there are very nominal fees, so you can join us to empower yourself in terms of your business network, in terms of your knowledge, in terms of your reach to the industry. So thank you very much. Any final words or statement from your sir, Murlikant sir? Then we will close the session.
Yeah, I thank you for this opportunity again. And each time try to come with a different experiences. And yes, the questions asked by some people are quite interesting, and I think I replied them in a reasonably satisfactory way. I look forward to do some more programs in the coming days. We share Delhi, and request Delhi to make it at least all India level, so that many people can be brought into the stream. Just only request from my side, just from my side, so that many people can be coming into, and the knowledge can be distributed even.
One more request: you can like our social media pages, Delhi Director of ISHRAE in Facebook and LinkedIn. All the programs is being updated in that platform as well, so you will be well updated in terms of upcoming programs, what we are going to do. So thank you very much. Thank you very much for joining the session.
Thank you.